My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I'd like to welcome you all to our International Physics webinar. And today is our 102nd International Physics webinar. And good evening to all. So hope you are well and safe from Corona pandemic. And all we know that we are staying in a Corona pandemic situation, so we cannot continue our normal academic program inside the campus. So we have to start our online program to continue our academic program. Our Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And we have successfully completed our 101 international physics webinar. And we try to involve the physicists from all over the world. And we are trying to adjust with this new normal situation. Today, it's a very important day for our department. And today, I'd like to welcome you all to a joint session between the Department of Physics, Pabna University of Science and Technology, and the Indian Association for the Cultivation of Science, Kolkata, India. And we have with us Dr. Utpal ChattopadhyayProfessorIndian, sir, Professor, Indian Institution for the Cultivation of Science, Kolkata, India. And he has already connected with us, so I'd like to welcome our speaker. So good evening, sir, and welcome to our International Physics webinar. And we'd like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology. So we have organized this program to for our students to encourage and motivate our students to in this Corona pandemic situation. For those who are new, I'd like to inform that we have divided our webinar into three parts. First of all, I would like to uh, introduce our speaker with all of you, and then our speaker will deliver his piece, and at the end, we have a discussion time. In that time, anybody can join with us. I think you have already come to know the title of this today's International Physics webinar, and our title is Supersymmetry in Particle Physics, and our speaker is Dr. Utpal ChattopadhyayProfessorIndian, sir, Professor, Indian Association for the Cultivation Science, Kolkata, India. So you can see his academic profile. He has completed his bachelor degree from St. Xavier College, Kolkata University, and MSc from Kolkata University, and PhD from Northwestern University, Boston, USA. And he joined as a senior lecturer at IACS in 2002, and from 2011 he worked as a professor there. So he also did his postdoctoral from the Tata Institute of Fundamental Research in Mumbai from 2000 to 2002, and also worked at the Harish Chandra Research Institute in 2002. He also worked as a teaching and research assistant in Northwestern University and University of Pittsburgh. We can see his area of research. His primary areas of research is physics of elementary particles in beyond the standard model scenarios like supersymmetry with emphasis on dark matter physics, electroweak fine-tuning or high-C problem in general, exploring issues on vacuum stability and stability against charge and color baking minima, constraining models through the flavor physics, precision test, and colloidal signal in general. Area of research, elementary particle physics, area in physics beyond the standard model, particularly involving physics of low energy supersymmetry, dark matter analysis, etc. We can see his Google Scholar ID, and you can see his citation number is 2799, and you can see his ResearchGate ID. His ResearchGate point is 31.75. So thanks all for all of your patience. Now it's time to go to our speakers. So sir, thanks again for accepting our invitation. So it's your time, so you can start your session, sir.
Thanks a lot. Good evening. And I thank the Department of Physics, Pabna University of Science and Technology. And I particularly thank Professor Pretam Kumar that he is working a lot regarding these, webinar activities. And I am sure this will help the students. And I wished that I would go to Pabna University of Science and Technology at some point, but right now it's not possible. And I am from actually.
I'll definitely invite you after the COVID, sir.
Thank you very much. And actually, my ancestor is from my father also came from Joshua, Norail, so it's not very far from Pabna that way. So yeah. So let me start with supersymmetry in particle physics today. And now this is a very vast topic, so I have to be selective. And to reach the basic level of Lagrangian, it takes some time. But anybody can ask questions anytime. So let me start now. So supersymmetry in particle physics, why this is important? Let me just motivate first with standard model. Whatever we have we should describe. Then whatever you don't have, then we will go for that. So success of standard model in particle physics. So standard model is extremely good. Of course, we have the full theory ready, because after the Higgs boson discovery, standard model is in a firm footing, because that was the last particle we had to discover, and it has been done. So it's a success story. Let me give an example. If you have this fine structure constant, which is proportional to charge of electron square, E square. So E square, basically you can say that, E square measurement. So in experiment, the inverse of fine structure constant is 137.035999157. And in theory, we have 137.035999049. So this is a remarkable agreement, and I don't know whether there is any other branch of science whether that can claim this kind of agreement of theory and experiment. So this is really great. So there exist many other superb agreements between the measured value and the computed values of physical quantities in SM, but we are just giving an example. Okay, let me go to the second slide. Radiative corrections to the Higgs mass. So let me, since this is a topic on supersymmetry, so we have to go to find some difficult areas of standard models where we have some trouble. Then the idea is we have to do some troubleshooting. That is the idea. So the trouble area, the Higgs mass self energy correction. So considering the only Higgs fermion interactions, you can see that Higgs mass square gets some quantum correction at one loop level, the basic level. So that is about YF, basically is Y top, or you can consider the top quark mass whole square. And then you have minus 2 MUV square. This is the ultraviolet scale. This can be very large, because after standard model we don't know any other physics. So it can go to the gravity scale, 10 to the 19 or 10 to the 18 GeV. So that's quite a lot of correction. So the correction MUV, you can see the scale of new physics that would modify the loop integrations. This scale can be as high as Planck's scale, that is 10 to the 18 GeV. A fine-tuning or cancellation out of a counter term that is as precise as 1 in 10 to the 33 is required to get the Higgs mass, the observed value, at 125 GeV. What is happening is this. You have this correction, very large correction. Now you have to add some counter term, the renormalization prescription. So the counter term should be also as large as this. So, and it has to be very precise. The precision level is 1 in 10 to the minus 33, at 1 in 10 to the 33. So that's a very precise calculation, cancellation. Now, if you require that, you are really doing a lot of fine tuning. I mean, unless you give that kind of value, your theory is not stabilized, and this is a very problematic thing. So this points out to the hierarchy problem we'll talk about, that is concerned with the weak scale to be much smaller than the Planck scale. Why? Because weak scale, where Higgs belongs, 125 GeV, that we know, that Higgs, W boson, Z boson, these are of 100 GeV order particle. And then you are talking about some correction that is about 10 to the 1 in 10 to the 33 level of precision, level of cancellation required. So very large correction. So if it is 10 to the 18 GeV, so 10 to the 18 GeV square, that kind of correction you are talking about. So this is a fine-tuning issue. And since it is fine-tuning, I can give you an example in a circus party. So you have an elephant which is standing on this roller. So this is very fine-tuned. Now, this is in contrast to fermions. Now, why is happening? Because standard model has a weakness in the scalar area. Higgs is the only scalar in standard model. So consider fermions. Fermions means quark, lepton. Now, let me just go back once more to introduce standard model. Like we have 3 quarks, 6 quarks, top, charm, up, and then strange, bottom, So 6 quarks, and the 3 charged leptons, tau leptons, mu leptons, electron, and then 3 neutrinos, tau neutrino, muon neutrino, and electron neutrino. Now, if I consider the top is the heaviest quark, so that has a lot of things to do with Higgs physics, because this will give you the lot of correction. Now, the Higgs physics is controlled by electroic symmetry breaking. Higgs potential, that is kind of a Mexican hat type of potential, and you break that potential with, essentially you consider VH with negative Higgs mass square, H square, negative Higgs mu square, H square, so something like square term is negative actually. So then I go to the next slide. So what I have seen that the electron is there, muon is there, and all the top, bottom, all the things are fermions. If it is fermions, do they require a large quantum correction? That is my question. Let us see. If you consider, say, electron, the electron correction delta ME, the quantum correction, is about 2 alpha em over pi. Alpha em is 1 over 137, say, and Me, the mass of electron, is small. The log of lambda and Me, because lambda is the highest scale. Highest scale means it can be Planck scale. So if it is Planck scale, then it's log of 10 to the 18 over Me. So whatever be this quantity, even if it is large, lambda is large, if you consider a logarithm, then it is toned down. So you don't have very large correction. And what happens, you see, delta Me, the quantum correction, is proportional to Me, the electron mass. And if it is so, as Me goes to 0, delta Me goes to 0. So there must be some symmetry. So what is the symmetry? It's called chiral symmetry between, say, if you have a Dirac electron, psi L and psi R. See, if you consider no mass for the Dirac equation, then you have a symmetry that's called chiral symmetry. So the symmetry is protecting electron. So symmetry has to protect gauge boson. That is the case, but we have not given an example here with diagram for gauge bosons. But the symmetry is not there for Higgs. So that is the problem. Now, that is the original motivation of supersymmetry. That's why we are spending some time on it. Am I audible?
Okay, sir.
So had there been a scalar loop, so let us consider that we have a loop in the Higgs mass correction. We have a top loop. The F is fermion. So the heaviest fermion is top, that is contributing the most. So if you consider top loop, that is this loop. So that is contributing this high value. Now let us go to an hypothetical situation. Instead of a top, if we had a scalar particle. If we had a scalar particle, then that would also bring mu AUV square, that large quantity. And that large quantity could be cancelled by this, if you consider both together, the scalar particle and this top loop, in the if you combine them. So this is, okay, I can show you. This is in contrast to delta MH square in the previous expression. The previous expression I had something like 2 MeV square over, and here YF square was 16 pi square, and so instead of 2 I have 1 here, although, but it is coming with an opposite sign. So this is negative because it is a fermion, and it is coming with a positive sign. Now, so is there any boson fermion symmetry, so that with equal masses lambda s equal to YF square, equal masses of bosons and fermions, like scalar mass s and the top mass. So if they consider to be equal, if you consider them to be equal, then lambda s equal to YF square, if you just take it this way, that is your assumption, and you consider two complex scalar fields, like S is a complex scalar field for a direct fermion, then we would get an automatic cancellation. So that is the catch. I mean, if we can have a theory that can have a scalar, complex scalar, we could have an automatic cancellation. So is there any theory? The idea is, yes, there is a theory, and that is concerned with the symmetry also. It's called supersymmetry. So let us pursue it. So to motivate why we should go to standard beyond some physics beyond the standard model. So SM has the standard model has large Higgs mass radiative corrections. That's what we told. No neutrino mass. We know that neutrino has mass. So, but SM doesn't say that. No baryon asymmetry. So, baryon asymmetry. Say if you consider proton, then you have antiproton. So we have plenty of protons. We are all made of protons, neutrons. But how many of us has antiproton? Probably nobody, almost zero. So we have lots of protons, but no antiprotons, and same thing for anything. No, so baryon is not, they're not equal. So number of protons is not same as number of antiprotons. So that's the problem. So standard model doesn't address that. What would be desirable to see in SM? A candidate for a particle dark matter. So SM doesn't have that. The SM has a product group, SU3 cross SU2 cross U1, which is not good for unification of fundamental interactions. Accommodation of gauge coupling unification at a high scale by RG running. You can see the figure actually. If you consider SM, these are the dashed lines. So 3 alpha 1, alpha 2, alpha 3. These are the 3 couplings like QED, then SU2 coupling, and then not QED, I mean U1 coupling, and then SU2 coupling, U1, SU2, and you have the SUC, the strong interaction coupling. So if you produce them up to the Planck scale, they don't meet each other. So U1 and SU2 meet at one point, but SU2 and SU3 meet at another point. So that is quite separated. So one is 10 to the 13 and one is 10 to the 16, something like that. But if you consider supersymmetry, then it is seen that they are coming from a single point. So you can really consider some models with supersymmetry with higher gauge group. So that will lead to standard model gauge group, and you can have gauge coupling unification. That is a good thing. So that is one thing. And there are many other issues on standard model, but we are not going to talk about them because of time. And then another thing is that some issues are not solved by supersymmetry, so why bother to discuss? Now, what is supersymmetry? So I will try to, because there are lots of theory behind it. So to reach the Lagrangian, it takes a lot of slides. So let me try to be brief, and if it is sensible, let me see. We have Poincare symmetry. So Poincare symmetry, like you have momentum, 4 momentum, that is there. This is based on standard model is based on Poincare symmetry. So we have no problem with that. So can we extend that symmetry to include something else so that we have new generators? Like for supersymmetry, one introduces fermionic generators. So these are Weil spinors, Q alpha, and extend the algebra as below. Q alpha and Q alpha dot is alpha runs from 1 to 2. And these are SL2C related thing, but I don't want to go to that technical thing. So Q alpha, this is a supersymmetric generator. So like the momentum generator is P mu in regular 4-dimensional physics Lorentz symmetry. Now here you have fermionic generators. So 2 fermionic generators is producing some anti-commutator and producing P mu. That's translation, and so on. So we have angular momentum, M mu nu, and then Q alpha. So this is the generator for supersymmetry. So Q alpha bar is the Hermitian conjugate. So let me not go to so much of technical details, but this is the thing. Now supermultiplet contains an equal number of boson and fermionic degrees of freedom. So it's a boson fermion symmetry. So supermultiplet is a construct. We'll come to it very soon. That contains equal number of bosonic and fermionic states. The simplest is the chiral supermultiplet, which consists of a Weil spinor with helicity half and a scalar field. And there is an additional Weil spinor with helicity minus half and another scalar. These two represents together. They may constitute a Majorana fermion, and a complex scalar field. So 4-dimensional case. Majorana fermion. So direct equation, those who remember direct equations, you have two solutions, U and V. So if you don't consider any mass, so that will produce the wild spinors, U and V, and then you can consider Majorana fermion. Out of that, Majorana fermion is charge conjugate is same as the Dirac field. So vector supermatrix consists of massless vector boson. We'll come back to it, all the details. So let me not go to this description without mentioning so many things. It's not so important. We'll deal with superfield Sx, theta and theta bar. Explicitly, we will come to it. So I just wanted to give a hint because in case we don't get any time. So that's why I wrote something here. So what happens is we'll consider the superfield descriptions. A finite transformation generated by the SUSY generator P mu, Q alpha, and Q alpha dot is given by this quantity. It's like, if you consider a rotation, you have a generator, rotation generator, the finite generator. Then in a rotation, you have infinite amount of generator. So it's like that kind of thing. So G, X, mu, theta, and theta bar. Now, theta and theta bar, those are basically fermionic Grassmann quantities. So theta q, it means theta 1 q1, theta 2 q2. So theta 1 and theta 2 are Grassmann quantities, so anti-commuting objects. Then what happens is, if you consider two functions like this, so you get a translation x mu going to x mu plus mu, and then all this fermionic stuff, they also transform accordingly. So x mu theta theta bar goes to x mu plus mu, and this is the translation part, x mu plus mu minus the Grassmann quantity is giving this thing, and then this theta plus xi, this is because xi is appearing here. Okay, so these are added together. The superfield, what is because we will talk about superfield so much, so it's better to know what is going on little bit. What is superfield? So in general, this superfield, when acted on by the transformation, that goes S goes to x s nu s x mu theta theta bar, and then we have all this stuff. We'll define chiral superfield. That's why first we define the general superfield, then we'll go to chiral superfield. The generator of transformation can be written as, if you see, P mu goes to I del mu, and IQ alpha is del theta alpha. That you can always see here. So if you consider the effect here, you don't consider this xi here. So I sigma mu theta bar is there, and I theta sigma mu xi bar is there. Okay, so that this is like, if you consider rotation, you have a generator. You have a translation P mu, you have a generator. Then if it is supersymmetry, you have a generator also. So IQ alpha and IQ alpha bar. Now you can consider covariant derivative of SUSY algebra. So those are d alpha is del theta alpha. Now let me just mention carefully. Just 1 minute. This x mu and addition, x mu is a x1, x2, x3 and time. Now you are adding with theta 1, theta 2, and theta bar 1, theta bar 2. Those are Grassmannian coordinates. This is just a description. We are not dealing with actual Grassmannian coordinate with space-time. This is just for mathematics, nothing else. So we shouldn't think that this space has Grassmannian dimension, extra dimension. That is not the case. This is just for mathematics, nothing else. Now this is a very lucid description, that way you can give. So that's why we are writing. But there is an alternative way. You can we may not introduce any Grassmannian coordinate and talk supersymmetry. So a chiral superfield phi satisfies d alpha dot phi equal to 0. That's the definition of chiral superfield. So d alpha dot is defined as these. And as soon as you do, then you have some superfield, and you have y mu as x mu plus I theta sigma mu theta bar, and y mu as a phi as a function of y mu can be written as this. Now, why there is no other? Because it's like a series expansion. Now, why there is no other term? So this is the beauty of Grassmannian coordinate. Grassmannian coordinate, if you have theta 1 square or theta bar 1 square or theta 2 square or theta 2 bar square, that much you can go. But you know, if you I mean, theta 1 square is 0 actually. Theta 1 square is 0. So it can be theta can have theta 1 theta 2 and theta 2 theta 1. But if you consider c theta, say for example, theta. So you will come across with theta 1 square or theta 2 square, and it will go to 0. So in this kind of superfield expression, you can go up to theta term with this condition, this chiral superfield condition, T alpha dot. So that is there. Then in terms of, we talked about y mu in terms of x mu, so you can go back to x mu and you can get this term, theta term, and then theta bar term. So that is non-zero. Now let us consider infinitesimal SUSY transformation, under which phi transform as phi goes to phi plus delta phi. So delta phi means SUSY generators you have Q. So Q, and then it's like rotation generator, and you have the theta angle. It's something like that. So xi times Q, and then xi bar times Q bar. So that can be written as this way. So this leads to the following expression for the SUSY transformation. So SUSY transformation goes like delta phi is some Grassmannian quantity xi times psi, the field, and delta psi is given as that. So you have a complex scalar, you have a psi, the fermion, and then you have this is an auxiliary field. Auxiliary field is required because we had this in the expression theta. The coefficient theta, namely f, transforms as a total derivative. You see here delta f is del mu psi sigma mu xi bar. So del mu psi means it's a total derivative. And in Lagrangian formulation and in action, if you find, wherever you find a total derivative, you are safe because that will give you 0. Now, why you bother? Because if you have a transformation and if you see a total derivative, the transformation will not have any effect. That means there is a symmetry. The symmetry means you can do the transformation without any effect. So that is the symmetry. So delta f has this del mu psi, and that is a very important thing to construct supersymmetry Lagrangian. So products like this is very important point, phi I, phi j, and phi I, phi j, phi k. I mean, you have to do something like 2 pages of algebra to come to this result. Products like phi I, phi j, and phi I, phi j, phi k are also chiral superfields. We define chiral superfields, so they will follow that. However, if I consider 4 superfields, phi I, phi j, phi k, phi l, that will be 0 because of this Grassmannian property. Okay, so, and another thing is that this is not written here. I mean, I'm not sure whether you can read it. The last line is this: any holomorphic function is also a holomorphic function of phi is also a chiral superfield. So that's why we will talk about holomorphic function for potential. And then there is vector superfield. So vector superfield is defined as V is equal to V dagger, that is reality condition. So, and similar to that delta F, we will have delta D here in vector D, if you consider a SUSY transformation. Here also you see is a total derivative is there. If there is a total derivative, then you can construct a Lagrangian with the help of it. So you will have the symmetry, you do the transformation, the effect is, action is invariant. So there must be a symmetry. So that is the supersymmetry. And F term and D term, those are very important. Okay, so now this is another 2 pages of calculation. It's called Weiss-Zumino gauge that eliminates various spurious degrees of freedom in exchange of redefinition of components fields. So for convenience, we are going to one redefinition of fields, and we go to Weiss-Zumino gauge, that is theta theta bar v mu. This is the actual vector field, like you have mu, then w mu and z mu, like that kind of thing in the standard model. So it's the actual vector field that, and this is the vector superfield in Weiss-Zumino gauge. So that has this expression for in terms of theta, theta power series of theta. So advantages of Weiss-Zumino gauge is Vn Wz equal to 0 for n greater than 2. So we can do work with it for getting the kinetic term of the Lagrangian. So similar to F mu nu of QED, one quantum electrodynamics, one defines the field strength superfield W alpha for U1 gauge transformation as this is that thing. So we define D covariant derivatives, D bar and D alpha D, and that gives the field strength. So why this W alpha? So we'll see that this produces the kinetic term. Like kinetic term in QED is F mu nu F mu nu. So that can be generated out of this. QED is super QED. QED with partners of superparticles. Like electron will have some partners, electron, and so on. So W alpha is a chiral superfield and is invariant under general gauge transformation. Gauge transformation is important, so we want to preserve it. The construction of SUSY Lagrangian. So this is also quite detailed, but let me just go briefly. One has scalar potential that will give you the kinetic term, and one has super potential that will give you the potential term. So why D and F? Because this D term we already talked. This is the theta 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 bar term, and this is the theta theta term, like WF. So that gives the kinetic term and potential term. So in the simplest case, this is called Weiss-Zumino model. This famous Weiss-Zumino model. Then in the simple case, you can consider phi dagger phi, the D term, that means theta 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 bar term, and this F term, that means the theta theta term, you can construct the Lagrangian. And since capital phi involves small phi psi, the wild fermion, and then you have auxiliary field, you can go to L and expand this delta phi dagger, del mu phi dagger, del mu phi, and so on, so on. Then you will see that this F doesn't have any kinetic term, and since F doesn't have any kinetic term, we can also write F star is equal to minus W del phi. What is W? W is the superpotential term. Is a holomorphic terms of phi's. So this is a lot of detail. So what happens is you can get QED, the quantum super QED, basically quantum electrodynamics plus supersymmetric particles included. That way you can get the D term and the F term, and so. And you can also generalize to non-abelian gauge theory, and with this kind of transformation, V goes to TA VA, lambda goes to TA lambda A. So we get SUSY Lagrangian for the Yang-Mills fields. So that is the thing we require, because standard model uses Yang-Mills Lagrangian and then Higgs mechanism, of course, to give the masses. So SUSY Lagrangian for the Yang-Mills field, that's a basic building block of standard model. So that is kind of found with the inclusion of supersymmetry. So let me go now to something little little less mathematical. Now, what is MSSM? MSSM is the minimal supersymmetric standard model. Sorry that I didn't write the full. Oh, no, I wrote minimal supersymmetric standard model. Now, these are gauge eigenstates. What does mean that? So we have, this is the superfield Q hat, and you have the spin zero partner and spin half partner. So in the spin half partner, we all know this up quark and down quark. The left type means SU2, they transform Se to Se2L, and then they have a partner like squark. Sorry, yeah, up quark, and then you have up squark, and then down quark, and you have a down squark, and then you have a right-handed object, right-handed quark that doesn't go to SU2, so that transforms like U1, and then that's a singlet actually, and then you have a scalar, complex scalar UR star that contains a supersymmetric partner. So all kinds of things like you have electron and neutrino, they have a partner, electron and neutrino. Now Higgs, we need two Higgs. I will come back to very soon. In standard model, you have one Higgs doublet, but here you have two Higgs doublet superfields here. This is the hat is superfield, and then you have this HU plus HU0. These are not. These are Higgs zeros. These are Higgs zeros, so that is not available in standard model. But these two are also not available in standard model because instead of one Higgs, I have two Higgs doublets. And this gauge fields, like gauge field, what we have is SU3 gauge field gluon, that is in standard model. But here you have gluino, the spin half, and in standard model you have W0 and W plus minus bosons, and then you have W0 and W plus minus. And these are, I'm talking about fields, not the particles. And B0 and going through B field is going to B no field. So that is the idea. Now with that kind of idea, so since we know the formalism of this chiral superfield, how to construct the Lagrangian, and technically we are comfortable to get this Lagrangian, and then we can use this to go to beyond the standard model with supersymmetry. The Lagrangian of MSSM consists of kinetic and gauge terms, and terms derived from the superpotential W, and the softly broken supersymmetry part L soft. What is soft broken? Because supersymmetry, if you consider, that cannot be really, it expects that electron should have equal mass with electron, or muon should have equal mass with muon. So that didn't happen because we didn't see those particles. So what is happening is supersymmetry is broken. So like any symmetry that can be broken, like SU2 cross U1 symmetry is broken in standard model, here also we believe that supersymmetry is broken. Now, supersymmetry is broken with soft terms, breaking. Soft breaking means what? We remember that the Higgs mass loop correction, quantum correction, we had a MUV square, that is quadratic divergence. But then we had a logarithmic term. Let me go back and show once more what we had there. You see here this MUV square. This is a square, very large quantity. Then you have a logarithmic term. So soft breaking means we will not generate any quadratic divergence. We may include some log divergence. That is quite manageable. That is a very small number here that way. So in MSSM, we include soft breaking, soft supersymmetry breaking. So we allow supersymmetric particles to have little bit different mass, not little bit. I mean, if it is 1 GeV and then another will be 1 TeV, and then we do the construction. The superpotential that preserves supersymmetry characterizes the theory WS. What we have is Yukawa coupling, YU. We have same Yukawa coupling as standard model, but here this Yukawa coupling is a matrix, not like standard model. So we have all these fields as matrices. The field, super fields are matrices. YU is matrix, and then they combined with some SE2 prescription, and then you have H mu term, Higgs mass term, HU, HD. This is superpotential. So this mu is coming from, this is required later on, mu is coming from the superpotential, nothing else. The fields, superfields U hat, Q hat, and HU hat, etc., all chiral superfields that contain standard model and superpartner fields. Yu, Yd, Ye are 3 by 3 Yukawa coupling matrices, including all the generations of quarks and leptons. W is dominated by the third generation of because the large top quark mass. So Yt is large. Yt is proportional to Mt, the top mass. Top mass is about 175 GeV, and up quark mass is less than a GeV. So top mass is the dominating one in the superpotential. Both Hu and Hd superfields, Chiral superfields, are required unlike SM. This is required for holomorphicity of the superpotential, as we expressed that superpotential can be holomorphic with phi cube term only, and apart from anomaly cancellation, that is technical. I will not go into it. W refers to a version of SUSY that assumes R parity. This is extremely important. R parity to be conserved, like PR is minus 1 to the power 1 to the 3 and B minus L plus 2s. B minus baryon number, L is lepton numbers, and if you consider this baryon number and lepton number bookkeeping, all the standard model particles will have PR is equal to 1, and the super partners will have PR equal to minus 1. So this means that super partners are produced out of SM particles in pairs. Okay, so you have two super partners from one single particle, or a super partner will decay into a super partner along with an SM particle. Now, if the super partner decays into a super partner along with an SM particle, what happens to the lightest supersymmetric particle? The lightest supersymmetric particle cannot be decayed at all, so is stable. Lightest supersymmetric particle cannot decay. Well, that doesn't mean that it will be there forever. So lightest supersymmetric particle can interact with another lightest supersymmetric particle, and that two supersymmetric particle may produce something else. That's a different issue. But if you take a lightest supersymmetric particle alone, it will not decay. So if neutral, this may be a candidate for particle dark matter or weakly interacting massive particle wind. Am I audible?
Yes, we can hear you, sir.
Okay, thank you. So conserved R parity also avoids baryon and lepton number violations, thus giving stability to proton, because we know proton is extremely stable. The stability limit can be 10 to the 33 years. So you have to wait for a proton to decay. That is the experimental limit. It may be absolutely stable, who knows. So you have to construct your theory so that whatever you observe, that is respected. So proton decay is respected through this kind of construction, R parity, conserving supersymmetry. The super particles must be heavy, the SUSY must be broken, so we require L soft. That's what we talked about before. L soft means terms like supersymmetry breaking terms, but that will not produce any quadratic divergence. So essentially, I will not go into detail, but what happens if one considers a hidden sector. The supersymmetry is broken in a hidden sector. Hidden sector particles are, they have no connection with standard model particle, but that the breaking of supersymmetry in that sector is communicated to the visible sector through gravity or some kind of interactions. So hidden sector particles may have gravity sensitive, and standard model sector is gravity sensitive. So gravity may allow interact with them. So that is the detailed mechanism of supersymmetry, and minimal supergravity or supergravity in general, or there are cases like gauge mediated supersymmetry breaking, anomaly mediated supersymmetry breaking. They really deal with this kind of breaking mechanism, what is happening. But while we talk about MSSM, we don't consider the details of breaking mechanism. We just consider there is an L soft, supersymmetry is already broken due to whatever be the reason, we don't care. Okay, so that is the whole idea. Now in MSSM, what we have is L soft. Let us see, because the superpotential is once you know the standard model particles, the superpotential is sharing the same Yukawa coupling, sharing the partners, and adding the partners, super partners. So superpotential is easy to construct, but the supersymmetry model requires assumptions about soft supersymmetry breaking terms. So what are the terms we have? Is L soft is gaugino terms, like this Bino, and then Uino, and then Bluino terms. The trilinear terms means we have, these are all scalars. Unlike hatted field, here we are talking about scalar fields. Here this gaugino is fermionic field, of course, but this U, Q, Q, tilde, and all those tilde fields are, scalar fields. Scalar fields means visibly shows that, is supersymmetry is broken, because we are not talking about their fermionic partners. We are talking only about scalars, not fermionic partners. So it's visibly a description of broken symmetry, and that's why it's called L-soft. Then you have mass terms and bilinear terms. So L-soft has gauginos, scalars, and not their superpartners, and violate supersymmetry. And M square is 3 by 3 Hermitian matrices in Fermi space. Here you have some problem, because instead of a single mass like upward mass or top mass, you are bringing a matrix. So you have lots of matrix elements in the off-diagonal elements and diagonal elements. Well, diagonals are fine. What about the off-diagonals? Well, off-diagonals are strongly constrained by phenomenology, like Weber physics and other things. So we should not worry too much about off-diagonal entries. So diagonal entries are more important. And A is a trilinear coupling matrix. So that is the soft term. Now simplifying assumptions, like whatever I was telling, the constraints from Kleber changing neutral current efficiency and CP violating effects strongly limits the parameters. So simplifying assumptions, you consider diagonal masses, like don't consider up diagonal mass. So you consider all things diagonal. So depending on the type of SUSY breaking, simplifying relations at a high scale, like that of the unification of gauge coupling scale, 10 to the 16 like gauge coupling unification we showed. So 3 couplings are unifying at some scale like 10 to the 16 GeV. There you can give these masses, and if you give these masses to that scale, then you have to use renormalization group equation to come to the weak scale. And now in the GART scale, I mean this is called GART scale. In the GART scale, you give few parameters like 4 or 5 parameters, and all the off diagonal, including diagonal masses, are generated out of renormalization group running, because renormalization group relates one scale to the other. But in MSSM, when we are studying MSSM, we are giving every masses at electric scale. There is no question of electric RG running. So in any case, I mean, if you consider M Sugra or C MSSM from the constant MSSM, those are the versions where you give masses, the simplified masses at the GART scale, let's 10 to this 26 GeV, and you use RG to evolve to the weak scale 10 to the 3 GeV or 10 to the 2 GeV. So in models like minimal supergravity, we can have definite values for common gaugino, scalar, common trilinear parameters, all given at the scale mu. We can assume values of phases appropriately to avoid problems due to CP violations. So we are not going to deal with this. So now let us understand what type of particles we have. We have to understand, because we will talk about dark matter a little bit, and we have to know what is neutralino. Neutralino is a mixture of gauginos and Higgsinos. Gauginos and Higgsinos, they share common quantum numbers, and that's why you get whenever you have a mixing, you have a matrix, and you have gaugino M1, U1 gaugino, this is M2, U2 gaugino, and these are Higgsinos, minus mu. There are 2 Higgsinos. So mu, and what happens is, if mu and M2 are large, the lightest neutralino, I10, is almost a bino. So whatever with among these diagonal elements, M1, M2, and these off-diagonal elements, mu, minus mu and minus mu both, if you consider one of them to be the lowest, so neutralino lightest, I10 is the lightest, neutralino lightest will be of that nature. That means if mu and M2 are large, then that means M1 is very small, so the neutralino will be bino-like. Smaller mu means if mu is the smallest among these 3, then it will be a Higgsino-like. So it matters, because the dark matter properties are related to whether it is bino, Higgsino, or Wino. That is the idea. And similarly, we have charge Winos and Higgsinos. They mix also, and they produce charginos. So like W plus minus bosons, So they have partners. So here you have this kind of charges. Sorry. If mu is large, the lightest here also. If mu is large, the lightest charge is the M2, we know like, and vice versa. And then you have quarks, quarks superpartners, quarks, and then lepton superpartners, leptons and neutrino. So they mix here. So this mu quad beta is coming from the superpotential, and this AU is coming from the soft terms. And MQ squared, this is the left-handed coax superpartner MQ square, scalar partner, that kind of field, and they mix together and they produce the, say for example, top quark mass 1 and 2, MT1 square and MT2 top quark, not top quark. That can be calculated this way. Similarly, leptons, like electrons, instead of electrons, you can calculate lepton mass. And in standard model, you have only one neutrino, left-handed neutrino. There is no question of right-handed neutrino. So there is no question of mixing here also. So you only have one neutrino. Okay. Then the among the spectrum, we have to talk about neutral and charged Higgs bosons. So charged Higgs bosons, there are 5 Higgs bosons. That's CP2, CP even neutral Higgs boson, HH, and then one pseudoscalar Higgs boson that is also neutral, and 2 charged Higgs boson, H plus and H minus. Typically, all other Higgs bosons except small h are quite heavy. And Higgs mass loop correction. Let us go back to the real thing, whatever we had. We computed Higgs mass loop correction in standard model. We found a quadratic divergence term. Here, if we consider Higgs mass supersymmetric loop correction, supersymmetric correction means you have top quark loop and you have the partner stop quark loop. So stop and top loop together, you see there is no quadratic divergence. You have only log term is coming. So there is no quadratic divergence. And if I plot AT versus MH, the Higgs mass, you see is an oscillatory behavior. And this oscillatory behavior goes up to say 135 GeV or so. So MSSM predicts actually that upper limit of Higgs mass is 135 GeV. Now that is a big thing, because why is big thing? In standard model, there are many issues like vacuum stability and other things. They were saying that depending on the top mass, the Higgs mass can be anywhere. So, but Higgs mass can be anywhere, heavy or less than 130, more than 130. Lots of predictions. I cannot go into those. But if it is anywhere, then you are finding the Higgs mass at 125 GeV experimentally. And this M small h is a standard model like Higgs boson. Among these 5 Higgs bosons, this is the standard model like. And you have exactly found 125 GeV, and this model is predicting 135 GeV. So that's a remarkable thing for supersymmetry, and we cannot really forget it. So this is one of the plus points of supersymmetry, I would say. Now, radiative symmetry, electrolytic symmetry breaking is another thing, theoretical issues. Like you can consider superpotential, and then you can consider the scalar potential out of it. And when you consider the scalar potential, you have the superpotential term mu square, and then the soft term MHU square. They merge together and they give Higgs scalar fields. These are neutral scalar fields. And if you have a neutral scalar field like standard model, you have to minimize it. And if you have to minimize it, then mu square is this and sine 2 beta is this. Now, what happens actually, if you consider the Higgs potential, you remember standard model, you get a negative, you need a negative mass square for the Higgs field, Higgs potential. Mass square term has to be negative. But there is no reason it was ad hoc, because you need spontaneous symmetry breaking, and for spontaneous symmetry breaking to occur, you need a negative mass square. Okay, so there is no other explanation. Now here in this theory, we get a regular explanation, because mu square is related to the soft mass square, and the Higgs mass scalar potential will automatically get the negative mass square required for electric symmetry breaking. So the supersymmetry breaking effect coming from MHU square, MHD square, they are producing this MH. What happens actually? MHU square RG turns negative at the weak scale. So this RG running, or rather than this soft breaking term, this breaking of supersymmetry is communicated to electric symmetry breaking. So this is I would say, it's a quite profound thing. So you have a reason for electric symmetry breaking. So electric symmetry breaking is broken radiatively rather than via an ad hoc negative mass square term in the Higgs potential. Now there is another problem, mu problem. Mu problem is this mu is supersymmetry preserving parameter. Why preserving? Because it came from the superpotential that preserves supersymmetry. And this MHD square, MHU square, these are supersymmetry breaking parameters. So we are combining these two sectors. One is preserving and one is breaking together, and you are getting a relationship. So that is a problematic thing for supersymmetry. But there are various other models like NMSSM, etc., next to minimal supersymmetry model. They can address all these issues, but we are not going to go into it. Okay. Now, how supersymmetry is seen, can be seen in the LHC. We have not seen supersymmetry yet. So, in collider situation, we can have two gluon producing, two gluinos exchanged by gluino. Then two gluons will produce two gluinos in the S channel. This is T channel. Then two gluons is producing two squarks. Then two quarks, one quark and one gluon is producing one squark and one gluino. So there are many ways you can deal with. To produce supersymmetry, you need very high energy accelerator like LHC and beyond that. So you need very high energy because these gluino and other particles like squarks and charginos and neutralinos, those are heavy. So if you have a heavy particle as outcome, you need a heavy, large energy collider. And LHC, probably we thought that in LHC we'll see supersymmetry. People used to bet maybe, but that didn't happen. But that has not. I personally don't believe that it has died. LHC may not be sufficient. LHC may not have the sufficient energy to see supersymmetry, but we have a long way to go because LHC will get upgraded, and time will tell. So this is the production of supersymmetric particle. Then you have typical signatures. How can you really see? You cannot really see the supersymmetric particle by itself. So what you have to see, because they decay very soon. So if you have P1 and P2 in LHC, the two proton collision, they can produce chargino and neutralino by some means, second lightest neutralino. And the second lightest neutralino will go to a lepton, and then another lepton, and then this all kinds of breaking, the decay chains you can have. So in this situation, we have 1L, 1L, 1L. So Cl, and this, if it is the lightest neutralino, this has no charge. This is only weakly interacting. So you cannot really see in the collider. So this will go as missing energy. So you do the bookkeeping for the energy, missing transverse energy actually. So C leptons and missing energy. So there are many ways to produce. The decay has leptons or neutrinos. So this is leptons. This chi20 is producing lepton and slepton. Slepton is producing another lepton and neutralino, and so on. And here this is different. Chi20 is producing slepton and slepton and chi1 plus is producing a slepton. So you have, so one is by neutrino, one is by two sleptons. And decay via gauge bosons also can happen. So chi20 and chi1, chargino and neutralino, they will go to decay to neutralino and Z boson, W boson. W and Z, those are unstable particles. They'll go to leptons again. So Z will go to two leptons, and W will go to one lepton. So you have again C lepton plus missing energy. Now missing energy there here, it means that neutrino is there also. So W will go to lepton and neutrino. Now So far for the collider. In collider, we have not seen anything. So there are bounds given by LHC people. We have not seen yet. Now, let me go to the dark matter front. Pretam, I mean, how much we have time we have?
Okay, so we have about 10 minutes.
10 minutes. Okay, let me try to finish. Rotation curve of galaxies. So we have seen that, the supersymmetry particle like light is neutral, or there may be some neutrino also. Neutrino is charged, less, no charge. So dark matter particle shouldn't have any charge. That is important, and should be stable. That is another issue. And let us see briefly what is there. If you consider two galactic rotation, I mean galaxies rotating along, two galaxies are rotating around each other. So we expect that this Keplerian motion, the velocity should go like gm over r root over. It's like mv square over r is g m1 m2 over r square. That kind of Newtonian velocity. Now you would expect that the velocity should fall like 1 over r square root, but that is not happening here. You see here the velocity curve is not falling. This is expected. You expected initially, but in the velocity curve is that are rising or flat. So if I consider it to be flat, what happens? So if it is need to be flat, then v is constant. That means m has to go like m proportional to r, or you can precisely write this way. So rho has to go like 1 over r prime square for flatness. So how this happens actually? If I go to the outer layer of galaxy, like say very far from the galaxy, one of the galaxies, even the stars around that galaxy will rotate like this behavior. Because if I go to the outermost layer, I expect that it should follow the Keplerian law, but that is not happening. Still, there is enough dark matter, and that is causing, probably causing. We don't know. We have not confirmed dark matter. So dark matter exists actually, and at least I believe that there are modified Newtonian gravity explanations of dark matter. Like if very crudely speaking, you have m1 m2 over r square. Instead of r square, you consider r2 plus some delta and try to explain. But as far as I know, the general feeling is that dark matter exists. It's not a question of modified Newtonian gravity unless you go to higher dimension theory. But I'm not an expert on this, so don't counter all these statements. So let me go to the dark matter explanation without considering changing Newton's law. So many candidates for dark matter, we focus on particle dark matter. And for example, instead of particle dark matter, there could be black holes, primordial black holes. They don't produce light. So that could be a dark matter candidate also. But since we are doing particle physics, we stress on WIMP, the weakly interacting massive particle, and supersymmetry provides that. So we focus on particles. Neutrinos can be hot dark matter. Hot dark matter means relativistic dark matter. Structure formations, galactic structure formation is likely to prefer cold dark matter, that's non-relativistic particles. Now neutrino can be a particle like that. Supersymmetry gives a candidate for weakly interacting massive particle, WIMP type of dark matter. Apart from gravity, WIMPs may interact only weakly, weak interaction. So weak interactions and WIMP miracle is, what is WIMP miracle? Let me see. The dark matter has some, relic density. So dark matter is hanging around over the space, and that has, kind of density. You can find some density through Planck result or something like that. Experiment. So that kind of density, if you require, that is omega is some measure is 0.112 or whatever. So WIMP miracle is like that. If you consider weak interaction, the weak coupling, and the WIMP mass, they are conspiring in such a way that you are producing the correct relic density. So you are shooting the bird in, you are doing solving the problem in two ways. One is you are solving the hierarchy problem, like Higgs mass radiative correction through supersymmetry. And supersymmetry is producing another miracle that, you have weak interaction, you have right kind of mass for the particle with weak interaction, so that produces the right amount of dark matter. So that is called WIMP miracle. So the dark matter, amount of dark matter is amazing. If you consider this is the dark matter 0.112, baryons is about 0.022, whatever we are made up of. So you can see here, this is about 27% about the whole universe, and this is 4%. I cannot see properly. So, this is a huge difference between matter and dark matter. Dark matter is quite large. Dark energy is a different story. We'll not go into it. So that is the dark matter thing. Now there is another explanation like bullet cluster. So it is hard that modified Newtonian gravity Mond will explain this bullet cluster, because this is quite. Bullet cluster means cluster of galaxies colliding together. So two things happens. You can consider gravitational potential energy, potential amount. You can have contours. Okay, so you can find the gravitational find this by gravitational lensing, like light bends around the gravitating objects. So from the light bending, you can see how far mass is there. Okay, so now light depends on dark matter particle, and because it's gravity, so dark matter and baryonic matter both will attract light that way. So like gravitational lensing. Now before and after, so this is the collision before the collision, and this is the after collision. So after the collision, what happens? We have X-ray emissions for the gases. So that is, and what is seen actually, the dark matter are not really colliding, they are just passing through each other, and the collision is given by the hot gas. Okay, so considering these gravitational equipotential lines, gravitational lens doesn't follow the baryonic matter but show strongest effects in two separated regions near the visible galaxies. So each is also shows the exact existence of collisionless dark matter. So this was there in 2006, I guess, but there may be some more experiments. Now, I'll quickly go through this thermal equilibrium annihilation process. So in the very early universe, when the temperature was very large compared to the supersymmetry particle mass neutralino, then what happens? Annihilation of neutralinos will go to standard model, and production of chi's from also standard model particles. So it's quark, antiquark, quark, antiquark, and lepton, antilepton. They are also producing supersymmetry particle. At the same time, WIMP is also producing standard model. So those are, the temperature is so high, that's no problem. Then annihilation era. So when T is much greater than m chi over 10, not m chi, the annihilation dominates, since standard model particles are not that much energetic to produce the WIMPs, those are massive. And the freeze out error is T is m chi over 25 or something like that. These are the errors here. So there, the annihilation is ineffective because the dilation happens due to expansion of universe. So you have dark matter particle hanging around, and the universe has expanded. So those particles are hanging around, and they are producing steric density. So that is the thing. Now, how one computes? One computes the sigma effective V, where V is the relative velocity of two annihilating WIMPs, and sigma effective V is the annihilation cross section to all final states. Okay. I mean, annihilation cross section of, say, for example, two WIMPs producing standard model particles. So that's what we calculate. Now there is co-annihilation. So co-annihilation effects needs to be incorporated. This arises from annihilation of WIMP with another particle with nearly degenerate mass. So if they have some particle interactions, so neutralino with some other particle, they can interact, and they'll also reduce the number of neutralinos. So that way, steric density is affected. Now, what are the processes? Like neutralino, for example, WIMP is neutralino in our case. Two neutralinos are going to FF bar, fermion and antifermion, and exchanges fermion, like electron or electron and positron. And then this happens for Bino like of neutralino, and this is like Bino like of neutralino with some Higgsino content. They can go to Higgs in X channel and produce FF bar. This Uino like of neutralino can produce two W boson, W plus, W minus, and they in turn can produce electron and positron. So you can have positron flux out of it, and they can also go to Z bosons. So those are relic density annihilation processes, and then co-annihilation processes. I don't want to go. Neutralino is working with lepton and producing lepton and Z or gamma, and so on. So there are lots of business with these dark matter people. Now, WIMP strategies, how we can search WIMPs. So early universe indirect detection, okay, I will come back to later. Direct detection of recoil of electrons. So consider that the dark matter particle will come to some xenon nuclei or some other nuclei, and then they will scatter. So the nuclear scattering will give some recoil, and you consider the recoil of nucleus to get that scattering effect, and you can put bound on it. And then collider search, you can have collider search in this WIMP search collider. And then early universe indirect detection, these I will not go, but briefly, what happens that this relic density mechanism is also true in galactic center or some planets, I mean some stars, inside stars. So the gravity may attract dark matter particles inside the core of the star or core of the galaxy, and there this WIMP, like neutralino, two neutralinos, will give an annihilation mechanism, the same annihilation mechanism in a very hot environment, of course, unlike present environment. I mean, in a very hot environment, but at present. So they can produce some gamma ray and other particles, so you can have indirect detection. So, and direct detection, the way it happens is like this kind of interaction, quark and anti-quark and neutralino and neutralino gamma mu gamma 5 interaction. This is spin dependent, and this is spin independent scalar cross section. So these two times, spin dependent and spin independent cross sections separately, alpha 2 and alpha 3I are the appropriate couplings. The above is summed over all quark flavors. And why quark flavors? Because you have proton or neutron only. Okay, so U and D quark. But all other quarks are happening because not only the valence quark, the C quarks, they also contribute. So you have to consider all that types. So it's a very detailed thing. The scalar cross section depends on T-channel Higgs exchange diagram. Here you have seen T-channel Higgs exchange diagrams, and the S-channel quark exchange diagram, like this one. Unless quarks masses are very close to the mass of LSP, the Higgs exchange diagrams usually dominate. This diagram dominates for direct detection, and we have not seen yet any dark matter evidence through direct detection yet. And there are possibilities like finding blind spots, like two Higgs exchange, they canceling each other, interference effect or something like that. There are lots of activities in this area, direct detection of dark matter. Now these I don't want to go. These are nuclear physics effects, because you are calculating quark WIMP scattering. Then you have to go to proton WIMP scattering. Then you have to, from proton neutron, you have to go nucleon WIMP scattering. So there's a lot of activity here. I mean, a lot of analysis that will give you the basically the form factors things. So how to calculate those details. So I don't want to go into that. Let us concentrate on only quark nucleon scattering, because the experimentalists give those scattering limits. So that's no problem. So spin independent and spin dependent. The direct detection of dark matter, some kind of results. So the Higgsino type of dark matter. So this means this lower position. These are the parameter points. Those are still surviving, and whatever you have before Zener 1T above, those are ruled out. So, and then I have chargino coannihilation, like neutralino and chargino coannihilation, that kind of scenario. That means that kind of M1, M2 mu possibilities. So you consider those, and then you calculate the scattering cross section, and you can rule out some parameter points like upper point, and so I don't want to go into that. And basically, then I will not go into this detail, but recently, I mean, the Fermilab is doing the experiment for mu1 g minus 2, and supersymmetry can give large effect in mu1 g minus 2. And this is a little bit outdated, 29.3. This is about 2 to 3 years ago. This number is there. So, but this is a little bit more. But nobody has given any explanation from standard model whether this really happens. I mean, mu experimental, mu. So 3 sigma, something like 3 sigma discrepancy between the experiment and theory. And supersymmetry can provide, and it seems like standard model result is getting stronger and stronger. I mean, reliable, more reliable. So that way, there is a high chance that there is a discrepancy, real discrepancy between experiment and theory, and supersymmetry can help to justify that discrepancy with large tan beta like VU or VD, that's tan beta, the Higgs waves VU and VD. So I don't want to go any further. It will be a matter of celebration if SUSY supersymmetry is discovered in colliders in the near future. It will show, or rather confirm, which direction to follow in particle physics, particle astrophysics, as well as grand unification in cosmology. So supersymmetry, we are just really waiting. If we see, I mean, it will give some direction, and lots of people are working, and no other beyond the standard model. I mean, no beyond the standard model has been stabilized that way from the experimental side. So nobody is sure, but supersymmetry, at least it relies on a symmetry, and very fundamental symmetry like fermion and boson. So why there is a fermion, why there is a boson, and why shouldn't be there in a symmetry. So it addresses that. And one thing I forgot to add, that the supersymmetry algebra is the only algebra you can extend to Poincaré algebra. So this is very theoretically motivating. So that's all I have to say. Thank you for all your attention, and sorry for that technical mishap and that delayed everything. Okay.
Thank you, sir, for your nice presentation, sir. So we have got some question in comment and in inbox. So if you allow, we can start the discussion session, sir.
Yeah, sure.
So the first question: can supersymmetric particle interact with another supersymmetric particle?
Sure. That's what we saw. Like, for example, neutrino is co-annihilating with chargino. So chargino and neutrino both are supersymmetric particles. They are producing some other particle, standard model particle. Yes.
Another question in the inbox: so why do we get asymmetry between the particle and antiparticle in the universe?
That is not known. Yeah, absolutely. This is a fundamental question, but nobody has known. Nobody knows. Even John Ellis doesn't know. So who am I?
Yeah, we are trying to understand.
Yeah, exactly.
So there may be another question. What is the superpotential?
Superpotential is kind of is a construction. If you want to construct the Lagrangian of supersymmetry, you have two ways. You can consider fermion and boson, and you add in proper number of fermions and proper number of bosons, and you construct supersymmetry. Another thing is that you use superfield formulation. Superfield formulation was provided by Abdul Salam, basically Abdul Salam and others. So he was an expert in supersymmetry. So this superfield formulation amazingly simplifies the calculation, and the superpotential basically is an expansion over fermion and bosons. Okay, superpotential contains is a function of some field phi. So the phi is a function of fermionic field and bosonic fields and auxiliary field. Okay, so if you consider then this auxiliary field F term that is multiplied with theta theta to give you that Lagrangian, because F remains invariant. It produces a divergence-less term. So that way, basically, what is called del mu something. So del mu something that is symmetry is preserved that way. So you consider that F term. So what you start with a field chiral super phi, you consider a superpotential, and then you consider the F term, and from that F term, that's theta theta term, you get the potential. So this is a mechanism to get the potential. Say, for example, you want to get the potential of QED, potential of QED in standard model. So electron is interacting with photon, okay, and electron has mass term through Higgs mechanism. So all these things can be done from the superpotential itself. So this is a technique that will not only give you the standard model potentials, it will give you the supersymmetry particles, included in it. So superpotential is a technique which will give you the required potential in the Lagrangian through this mechanism theta theta and theta theta theta, not theta 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 theta, but so one is called F term, one is called D term. So superpotential will give you the potential, actual potential, what you will use in Feynman rule through this theta theta term. So this is just a technique.
Thank you, sir. And this may be the last question, sir. Sir, do Maxwellian distribution exist in early universe, particularly in quark-gluon plasmas?
If it is very hot, I don't know, because I don't work in that area, so
Yeah.
I will refrain from answering this question.
Thank you, sir, for your nice presentation and wonderful discussion session, sir. We'd like to say thanks again on the behalf of the Department of Physics, Pabna University of Science and Technology, sir. I think, sir, our students have learned a lot of things about the supersymmetry in particle physics, and hopefully they will feel interest in this field in future. So thanks again, and if you have a time, we'll arrange another webinar with you, sir. So and hopefully after the COVID, I will definitely invite you.
Yeah, thanks. I love to go there. Yeah, I love to go there, and thanks a lot for all your endeavor, because you are taking an amazing amount of effort, and this is helping a lot of people. This is something everybody should try to do, but you are able to do it, and this is.
Thanks, sir. It's my pleasure and honor, sir, actually, to host.
And also, I'm honored to give this talk, and thanks for inviting me.
Yeah, thanks again, sir. Bye for today. Good night, sir.
Good night.
See you very soon, sir.